Just to level set on this, this talk takes a little over an hour, under an hour and 15. I recognize that may be a little bit much for lunch, but it is being recorded. And the last section is a performance comparison. And I'm also focusing today on Redshift and Athena, which are two AWS services that really target the same space, big data analysis, but take different approaches to doing it. Redshift has been around for, I believe, 10 years now, and Athena for, I think, 6. So before we get underway talking about those specific environments, I want to start with a few definitions. And the first is logical design. And logical design, as I say here, is the relationships between the business entities. So your customers have accounts, accounts will have transactions. And it's really how your applications deal with data. And generally, the logical design is developed by your application developers. Larger companies may have data modelers or business analysts who also participate. And one of the key things about logical design and why I call it out is that it is really independent of whatever database you deploy on. What's not is the physical design. And physical design, historically, when databases were rare and expensive, you had a team of database administrators who would work with the application teams to take the logical design and apply it to a specific architecture platform. And there are many different levels of physical design. At the top level, it's your table definitions and the types, knowing that Postgres, for example, has a text type, whereas other databases have varchar. Diving into it, however, is where things get really interesting. For example, knowing that MySQL, your primary key is clustered. So if you have a logical design that has accounts and transactions, you could improve the locality and therefore the performance of your queries with MySQL by actually adding the account ID into the transaction's physical primary key, even though it's not necessarily part of the logical primary key. And as you get really deep, you get into moving data between different volumes, indexes based on workload, and actually looking at the storage characteristics for your database. And I want to focus on that because that's really what I'm talking about, looking at how these two database systems, Redshift and Athena, manage their storage and what you can do to improve their performance. And the last definition, which here is a little bit snarky, is what is big data? And I want to tell a little story going back to my first big data project in 1992. A former coworker called me up and said, "Hey, we have this project here at Fidelity Investments where we're combining all of our customer retail data into one database that we can use for customer analytics and marketing purposes, and thought you might be interested in it." And I was, and we talked a little bit, and then I asked, "So are you running this on Oracle or Sybase?" And the person I was talking to kind of laughed at me and said, "You know, Keith, there's no Oracle system on this planet that can handle this data." And what they were using, what made the project really interesting to me, was a massively parallel database system that had custom hardware and SQL implementation to really be able to parallelize its database queries. And at the time I actually left the project 4 years later, we had 64 nodes. The machine cost $3 million. And with all of that, our active data set was somewhere in the 70 gigabyte range, which today I could run, maybe not with great performance, on the laptop that I'm using to give this presentation. So for me, big data is more about the sorts of queries that you do. And the first is that big data has a lot of table scans, which are absolutely forbidden if you're doing a transactional database system. Transactional systems are all about minimizing the amount of data that you're dealing with. So you may have 1 million customers who have 10 million accounts who have 1 billion transactions in total stretching over many years. Uh, but your line of business systems, your transactional systems, customer logs into the website and you make a query that retrieves their list of accounts. Any given customer might only have a half dozen accounts, probably fewer. When they look at an account and look at the transactions for the last month, typical retail customers might have a couple dozen, business customers might have 100. So you have these large databases, but at any given time, you're only touching a very small amount of them. And a lot of the physical design work to make transactional databases work is all about proper indexing, minimizing the actual amount of data you touch with any operation. And by comparison, uh, a big data analytics database, you might say, show me everybody who has transactions over $10,000. And there's just no way to do that, create an index that would do that without making that index just so particular that it could only be used by that one query. And instead, big data tends to do table scans, reading all of the rows in the table to apply the where condition and figure out the results. Now, fortunately, one other characteristic, especially for business queries, is that they're often restricted by date range. So you don't find all the transactions forever that were over $10,000, but you might look at the last month for a compliance report or the last year. And finally, big data queries, in my experience, have a lot of fairly complex joins. You might have 4, 5, 6 tables in a join to pull different pieces of data. For example, the question of the customers with greater than $10,000 transactions, you're looking at the transactions table and then potentially joining through the accounts table and then finally joining to the customers table. And some of you at this point may be saying, wait a second, that's not how I think of big data. And this is kind of two different approaches to big data. The first is the star schema, which also known as an OLAP cube. And I'll be honest, I don't have a lot of experience with these star schemas other than kind of tangential to the work that I've been doing with big data. But the idea is that you have a fact table. You may have multiple fact tables that lightly aggregate or have individual pieces of information. So for example, I have a sales table, a fact table. Now my sales table probably has a date, probably has a product. If it's for retail sales with a large company, might have a store number, and then dollar amount and quantity. So now you can slice and dice that data any way that you want. You want to find sales by store over the past 12 months, very easy to do. And along with your facts, you have dimensions, such as your fact table might identify a store ID, but that store also has a postal code, state, maybe a regional manager or whatnot that you would also potentially use to slice and dice your data. And the name star schema comes from this idea that you have your fact table and then hanging off of it, you have various dimensions that look like a star. So as I said, I've done a little bit of work with star schemas, but that hasn't been the focus of my experience with big data. Instead, most of my experience going back to the early 90s is with big data using a relational database. And the reason that you do this, much like relational databases took over in the transactional world from the network and hierarchical databases that preceded them, is that you have flexibility with your queries. So for example, when I talked about joins, a relational database has sales tables and might say, okay, customer buys product A, what are the top 10 products that they buy within the next 2 weeks? And you simply can't do that with a star schema, but you can if you have relational data that you can join. So the last thing that I want to think about as kind of introductory material is the idea that Seymour Cray was wrong. And if you don't know who Seymour Cray was, from call it the late 60s through the 70s, maybe into the early 80s, he designed some of the most powerful computers on the planet. And the approach that he took was throwing hardware at the problem. So he used logic circuits that were high power consumption, but switched very quickly. He used a dedicated vector processor for performing math on multiple data items at a time. But he never went down the path, Cray eventually did, he never did, of massively parallel systems. And in fact, in the early 80s, massively parallel systems were starting to make their appearance. And he came out and said, look, if you want to plow a large field, what do you want? 2 big oxen or 1,024 chickens? And everybody had a good laugh at the time, but much like who needs more than 64K, it turned out to be very wrong. And by the mid 90s, at least, most of the most powerful computers in the world were massively parallel. And when it comes to big data, it's really the only approach that you can use. If you think of a terabyte of data, for example, now any one computer system uh, really caps out at about a gigabyte per second of being able to process data. And there's definitely higher bandwidths. My laptop has higher bandwidths, but if you look at it, it really caps out at about a gigabyte. And that terabyte of data at a gigabyte a second is 20 minutes to do whatever you need to retrieve from it. Versus if you divide it up between 1,024 processors, each able to read at a gigabyte a second, it takes them only a couple of seconds to get the answers and then combine them. And that's kind of a key point that I'm going to hit quite a bit in this talk, but you came here for specifics about Redshift and Athena, so we're going to move on to Redshift. And Redshift is what I think of as a traditional database system, meaning that it's self-contained. It's responsible for managing its storage. It has its own users and permissions. And the only way that you interact with it is via SQL. You can't get at the data any other way. And that's kind of one of the key differentiators between Redshift and Athena, as we'll see in a few minutes. So the architecture of Redshift is, as you might have guessed, based on multiple processors that do work. So inside of a Redshift cluster, and this is an old picture, but generally correct today. There are, of course, little changes at the edges, but you have a leader node, which is responsible for communicating with your clients. And the leader node is it accepts SQL queries, it parses them, and it packages up the jobs that are run on the compute nodes. And one of the cool things I always thought about Redshift is it actually creates and compiles a C++ program to do the work. The compute nodes are where everything happens. Each compute node, this is what's known as a shared nothing architecture. So each compute node works on its own data. It has locally attached disk, or in the newer Redshift clusters, claims on disk storage. And all the work happens, as I said, on the compute node. So, if you're doing like a scan of a fact table, so you're finding all of the total up all of the sales by product, by state, perhaps. Redshift sends that out to the different compute nodes. Each compute node has some portion of the fact table on it, and in parallel, they read through the fact table, do the aggregation, and then the leader node combines the results. Now, one really important thing about Redshift is that joins only happen within one compute node. So if you have two tables, the rows for those tables that get joined have to live on the same compute node. And again, you can parallelize out the join, but either you have to ensure that the rows start out on the same node, or Redshift is going to move them there while you're running the query. And that's something you don't want to do. So that takes me to the first knob that you can turn. Excuse me for a second. And that's table distribution styles. When you create a table on Redshift, you tell it how its data should be distributed. And the simplest, the default, is even, which says distributed across all the nodes. And this is appropriate for a fact table. It tries to balance the number of rows on every node and can completely parallelize simple scans. The pair or partner for even is all, which says you replicate the rows. And all is appropriate for a dimension table. Because remember, you have to have the rows that you join on the same node. Let's say you're doing a dimension table is store ID. You could have stores in an evenly distributed table. You could have rows for different stores all over the cluster. So either Redshift has to replicate the dimensions at query time, or you just want to tell it to replicate when you define your table. And these are kind of the two basic distribution styles appropriate to fact tables, not at all appropriate to relational data. For relational data, you want key-based distribution, which is you take one column and it's used to identify which node the row will be stored on. So if you look at a accounts table, count ID might be a valid way to distribute the data. Then transaction table, you would also want to distribute on account ID. So that again, the joins between one account and its transactions happen on the same compute node. And this kind of brings us to the first rule when you're designing for Redshift, which is if you're picking a distribution key, you want to distribute based on the columns that you join most frequently. And here is a typical logical design for our customers' accounts transactions. Every row table has a primary key that uniquely identifies the row in that table. Accounts has a foreign key to customers because one customer can have multiple accounts. Transaction has a foreign key to accounts, the account ID, because one account has multiple transactions. And if you set the primary key, the logical primary key is your distribution key when you're storing this data in Redshift, it means that every query involving two of these tables will require query time redistribution. And that's because, again, we can only join if you're joining customers to accounts, you have to join on customer ID. And if you've distributed customers on customer ID, accounts will have to be redistributed. And incidentally, it's almost always the larger table that gets redistributed. It's the table that will have the foreign key relationship. So instead, if you're taking a first pass, and this is only the first pass, you might say, okay, accounts and transactions are big joins. We're doing that all the time. So we'll distribute both of them on account ID. And now joins between those two tables can proceed in parallel. And you'll still have to redistribute anything that joins to customers based on customer ID. But oftentimes that's okay. Uh, you have to look at how frequently you do this redistribution and really how expensive it is. If you have 10,000 customers, maybe it's not so expensive. In fact, if you only have 10,000 customers, you could use an all distribution on the customers table so that it doesn't have to redistribute at query time. But realistically, you don't have 10,000 customers. You have some number of millions of customers. And you probably want customers, information about customers, to be in all of your reports. So in that case, it's time for denormalization. So in a transactional database system, you don't want to denormalize, very simply. The idea of denormalization is that you have two ways to get to the same piece of information. And inevitably, in a transactional line of business system, someone's going to forget to update one of those pieces of information. And now you have corrupt data in your database. For decision support, which is generally built from your line of business systems, not so important to follow that rule, because at least theoretically, you can rebuild your decision support system if you find you've made a mistake. Where denormalization is often very useful is with Redshift propagating a distribution key. So here we have our logical design, but if we know that we're going to be joining these tables all the time, we might want to distribute them on customer ID. And to make that work, we could have our ETL or ELT pipeline add in a customer ID to the transactions field. Now, for correctness, you would still need to do the join based on account ID, right? Because customer might have multiple accounts, you can't skip that step. But as long as your join condition also includes the customer ID, it's able to proceed in parallel. So these are kind of a big conceptual bit. I'm going to look at the chat for a second and see if there are any questions. And I don't see any outstanding questions, so I'm going to go back. Oh, oh, I'm going to go back to the slides. So this is kind of your first step, as I say, when you're designing your database and the physical design, picking the appropriate distribution key. So what happens if you don't? Well, at query time, as I said, Redshift will redistribute your data, and this is a more or less expensive operation. So you want to look at your execution plans, which we'll see in the next slide, for how it's doing distributions. And what you want to see is where it says it's not doing any distribution. Everything's happening in parallel, no redistribution needed. Sometimes you don't get that. And Redshift will have to redistribute one of the two tables. And the outer table is the left side of the join, the inner table is the right side of the join. Generally, with a typical business table where you have one-to-many relationships, it's going to redistribute the inner table, which is often the larger table. And it's going to ensure that it redistributes it so that it can join to the outer table. Sometimes this is unavoidable. If you've decided that for whatever reasons you don't want to add customer ID into the transactions table, then you can do joins between accounts and transactions with no redistribution, but you'll see redistribution if you join to customers. Sometimes you have multiple ways that you want to distribute. For example, you might have customers, you might also have households, and you might equally balance the number of joins between those. So there's really no point at creating a distribution key on one, because half of your work is going to have to be redistributed anyways, although there are certainly ways around that. The final is, the second to last is dsdist both. And this often happens when you don't pick a distribution key for your tables. And because, again, you need to redistribute to join, you need to join on columns on the same node, Redshift will redistribute both. If you see this, it's almost always a problem with your table structure. And you should go in and look at your table structure and say, okay, why am I getting this? There are very, very, very rare cases where this is a valid situation to be in with a join. One thing that's almost never is broadcasting the inner table. And this is what happens if you don't set distribution of all for a dimension table. It will broadcast it. But if you're doing a join, what this means is basically that it's doing a Cartesian join. It's taking the inner table, replicating it on all of the nodes, and then joining. It thinks it will be faster to join each row in the outer table to every row in the inner table. That's basically a Cartesian join. That's almost always a bad query. Going back to the idea of joining accounts and transactions, if you join just based on customer ID, this probably wouldn't happen actually. You're leaving out the account ID part of the join, which is critical information in the join. We'll see some cases where Redshift would pick a Cartesian join later on. So I'm going to go back and look for questions at this point. So no questions still. So let's talk about execution plans. And I've talked a lot about execution plans. And the way you get an execution plan in Redshift is to just preface your query with the word explain. And you get what initially looks like a wall of text coming out, something like that. And we'll go back. I want to talk about this query. So this query is appropriate for Clickstream data, the idea of data that gets generated as you visit a website. So this might be an e-commerce website, and you have, every time your users go to the product page, it sends an event back to your servers that are then put into a Redshift database. If they add the product to a cart, a separate event is sent back. And this query is a query that says, okay, what products do people look at but don't add to their cart? So for every product, it's going to aggregate up by product, uh, take the difference between the number of times people have viewed the product and the number of times have added it to their cart, and it's going to take the top 10. So it involves a join. As it happens, well, we'll look at the query. So I've cleaned up the actual execution plan a little bit. A normal execution plan also gives you some statistics about the number of rows and the width of each row, and this cost figure that even according to the Redshift documentation bears no relationship to reality. Sometimes that's useful, but to really understand a plan, taking it off is the best thing. And when you read a plan, you want to read from the bottom up. So here, the first thing that does is a sequential scan. Remember I said table scans are a big part of decision support queries. It does a sequential scan on the add to cart table. That's the number of, that is the inner join of this query. And it hashes the results. And if you're not familiar, a hash table is simply a way to do very fast matching for equality. Then it goes through a sequential scan of the product page table. And incidentally, the product page table has about 60 million rows. The add to cart table is, I think, 19 million rows. So, not really big data, but nothing to sneeze at either. And for every row in the product page table, it performs a join, looks in the hash table to try and find a row from the add to cart table. And fortunately here, we have both of them distributed on user ID. So if you look right in the middle of the query, it says we're doing a dist none for the join. Then it aggregates, it sorts by the distinct events, then it sends each node in the cluster, then sends its local results back to the leader node. And we're not distributed on product ID. As you can see, the query ultimately aggregates by product ID. So the leader node then has to merge the results from all of the compute nodes, and then it applies a limit once it does that. So, what's a fairly simple query, once it gets sent out to Redshift, actually has quite a bit happening under the covers. And sometimes things can go wrong. So I'm going to look for questions for a second. Nope, not seeing any questions. Good. So sometimes things can go wrong. And one of these is unbalanced data, where one node has more data than all of the others. And the biggest example of that I know of is, again, going back to my time at Fidelity in the early 90s. Fidelity had one fund called the Magellan Fund that for the previous 15 odd years, it had beaten the S&P 500 by at least double every single year. The fund manager, Peter Lynch, is a kind of a celebrity in the investing world. And as a result, perhaps half of our customers had Magellan as part of their portfolios. So if you wrote a query, sometimes it would try and redistribute based on the fund name or the fund identifier. And you'd very quickly realize that while we had this 64 processor, $3 million machine, each of those processors were just 8386s, which was like a desktop at the time. So looking for the execution plan, uh, making sure that you didn't have that redistribution was a very important task. Now, in a lot of data, you don't have a situation where users will have such a strange skewed distribution. But one thing that I've found is that if you distribute on a column that contains nulls, you can have a similar situation. And remember, you don't distribute on primary key. Primary keys can't be null. You're distributing on your join column, which could very well have nulls in it. And one example that I ran into a couple of years ago was the Clickstream data. I'm going to dive in a little bit more. When you first go to a website, it doesn't know who you are. So it's going to generate an anonymous ID to track your behavior over time. And it's going to send back events that have this anonymous ID. If you then log into the website, uh, it will have a user ID, a different unique identifier for you. And it's going to send back events that have the user ID and also, incidentally, the anonymous ID, so that you can see what people did before and after they logged in. Now, at this particular company, we wanted to pay attention to what logged in users were doing. So we did all of our joins based on user ID. And we kind of assumed, yeah, we're getting events that user ID is null. That shouldn't be a problem. Well, it turned out that a lot of our events were from people who hadn't logged in. And the way that you kind of see this happening, this is CloudWatch metrics, and most of this shows activity against our Redshift clusters. It's fairly normal. But if you look on the right-hand side, you'll see that there's a blue line that's significantly higher than the other lines. And if you look at the legend, you see that this blue line is compute node 0. Well, compute node 0 is where the nulls end up. And this particular query, which took approximately 45 minutes to run, did not restrict its join to cases where user ID was not null. So compute 0 spent twice as much time as everything else processing its results. Solving that problem was fairly simple. You just have to make sure that you have where user ID is not null if you're ever joining user ID. But there's an even more subtle problem with this, in that compute node 0 actually had more space taken up by these null rows. So this was an 8-node cluster, and nodes 1 through 7 had about 50% space utilization on their disks. Node 0 had 70% utilization. So node 0 pretty much capped everything else we could do. And the solution was basically to denormalize and have a distribution key that combined user ID and anonymous ID. And for most joins, this was fine. You just joined based on this combined key with an additional condition on user ID, and you got logically the same join happening, but you didn't have the situation where compute node 0 was doing all of the work. And then in the rare cases where you needed anonymous ID, you could basically do the same thing. So this is one of the things that historically unbalanced data causes problems for massively parallel database systems. And that's all I want to talk about for distribution today. What I want to talk about now is the other big thing that Redshift does for performance, which is to use column-oriented data. And I'll stop for a second and check for any questions. Nope. Okay, we might be going very fast. So traditional databases are row-oriented. If you look at like Postgres, and what that means is that all of the fields for the record are stored together, and then the records are stored one after the other. And there are certain optimizations that different databases use, but this is pretty much the way it works. So if you want to find everybody who lives in Illinois, for example, you start at block 0, row 0, and move your way through block 0, then to block 1. You have to read your entire table. Now, if you have a million customers, I'm going to make the numbers easier. You might have 512 bytes per row, so half a gigabyte of storage that you're going to have to read a block at a time to find all of your customers in Illinois. You could potentially put an index on that column, but again, for decision support, indexing often isn't used. The alternative, which Redshift uses, is it pulls out each column and stores the data for that column all together in the order of the rows. So here, the example I took shows social security number, which you probably don't want in your database, at least not a public database, a database that anybody can get access to. And instead of having the social security numbers separated by each row, it's one follows another. So in this hypothetical disk block, you have the social security numbers for all the rows of the table. So you just need to read the one chunk of data to find a social security number. In the case of state, you would have Alabama, California, Illinois, Pennsylvania, Massachusetts, Ohio, Illinois, whatever, one after the other. And to find all the people in Illinois, you just have to read the data blocks containing the state column. And if you have 1 million customers, you only have 2 bytes per customer. So 2 megabytes to find all of the people in Illinois. Much more efficient, and it's really dramatically more efficient. So that's a big optimization that Redshift uses and other decision support databases for performance. And you have a couple of knobs that you can turn on that. So the first thing is the sort key, and I've written a bunch of text here. Sort keys basically say that the columns that you specify in the sort key determine how the rows are physically laid out in the table. So going back here, if you had state as the sort key, you would have all of the Alaskas first, then the Alabamas, then the Arkansas, I think, all the way up to, if I recall correctly, Wisconsin at the end. And now, if you're going through the table, you can ignore all of the rows before and after the Illinois rows. So it's much less data. You might have 2 million rows, but if Illinois is only 10% of your data or less, or you might have 1 million rows, if Illinois is only 10% of your data or less, you're now reading rows, 100,000 rows. So much less data. Normally, however, my experience, you don't put a sort key on state. You want to put it on timestamp because most business queries are going to use timestamp somehow. As I said back at the beginning, find me all of the customers with transactions over $10,000 in the last month. As you get larger, you might find benefits to Redshift's flexibility of sort keys, but my recommendation is starting out, sort on timestamp. Then the other thing that you can do with column storage is you can very efficiently compress it. So for example, states take up 2 bytes each, but Redshift is able to actually use a dictionary style compression where you only have 60 or 70 state codes, including territories and Army PO boxes, military PO boxes. So you only really need 1 byte to store that data, and Redshift can do that. Uh, that doesn't seem like much, so you're cutting 2 megabytes down to 1 megabyte. Sure, it's less data you have to read. But certain fields, for example, your UUID is 40 characters long, but it has a very limited alphabet that it's used, basically 16 characters plus dashes. So if you turn on compression for UUID fields, it can actually reduce it down to about 8 bytes per field, which could be really pretty significant, especially with things like Clickstream Data that have a lot of UUIDs. All right, that wraps up Redshift. One more check for questions. Nope. So let's talk about Athena. Now, I had mentioned that Redshift is a traditional database, completely self-contained. Athena is the polar opposite. Athena is started out as a database architecture. It's based on the Presto database architecture, which reads structured text from files. In the case of Athena, those files are stored on S3. The controller is much like the leader node at Redshift in that it interacts with the client and is responsible for parsing your queries and writing it. Instead of having a built-in data catalog and permission structure, Athena goes out to an external data catalog. I know that it has one built in, but most people use the Glue data catalog, uh, which they can populate from a crawler over the data. So it goes outside of itself to look at the table definitions. It also relies on permissions, IAM as its permissions, the built-in uh, AWS permissions model, because it's accessing data from S3. So you're basically taking these functions that are part of a traditional database system and you're splitting them out. You can go to S3 with anything you like. You can write a Hadoop query to go against S3. You can read it, read the files individually yourself. So you're not restricted to using SQL. And the last thing that Athena has is it really embraces the 1024 chickens approach. I show 4 workers here, but the number of workers will depend on the size of your query. And Amazon doesn't document the actual relationship, but it appears to be based on number of files and the size of those files. So if you have more data to query, Athena will give you more workers to do it. Unlike Redshift, where you're fixed either the number of nodes for a provision cluster or the number of Redshift processing units for a serverless cluster. So different, different architecture, different knobs that you can turn. And the first of those knobs is file formats. And Athena supports a lot of structured text file formats. There are actually more than fit on this slide. JSON is fairly common, CSV, text files. One of the examples in the Athena user guide is using Athena to process load balancer access logs. Basically, it uses a regular expression to extract fields from the access logs, and now you can use SQL to query your access logs. I actually used this a few years ago uh, with a client that was having issues where some queries were timing out. So we could write a really short SQL query that goes through all of their access logs, finds the timeout, and shows what the path was that was used for that query. And they actually discovered from that that there was a backend service that was failing. But of these formats, if you're looking for performance, there's really only 2 that you want to pick, ORC and Parquet. And if you read the descriptions are identical. They're both columnar formats used by Hadoop. And to understand why there are 2 of them, you kind of have to understand the Hadoop ecosystem. And Hadoop came out in the mid-aughts from the Apache Foundation as a framework for doing MapReduce queries. Google had released their papers on MapReduce and everybody wanted to do it, and Hadoop was a way to do it. Unfortunately, MapReduce is really a painful way to do data analytics. So a lot of stuff got built on top of Hadoop, such as Spark, such as the Hive data store, and Presto. And at the same time, a lot of companies kind of went their own paths for doing their own data storage and integrating that. Some of those got integrated. So ORC and Parquet are 2 separate projects. One is, I believe, from Meta, formerly known as Facebook, and one is either LinkedIn or Twitter. And they're associated with 2 of the big consulting companies in the Hadoop space, Cloudera and Hortonworks. So you have 2 competing file formats that both got merged into the Hadoop core and are standard file formats for Hadoop. Of the 2, I've looked at the specs. I think ORC is arguably a better design, but Parquet is probably more popular. But regardless, pick one or the other. If you have data coming in as CSV or JSON, I strongly recommend that you use a glue script to transform that data into Parquet before you query it from Athena, because it really does improve performance. And the second knob you turn is picking the right file size. And there's a trade-off here. The larger your file, the less overhead. And you may think S3 is instantaneous, but it's not. It takes, give or take, 50 to 100 milliseconds to establish a connection to S3 and get byte number 1. On the other hand, if you have high bandwidth, which you do from Athena, it might take another 50 milliseconds to read multiple megabytes of the file. So you definitely want a larger file, and there's different rules of thumb that you'll hear from people, but between 50 and 100 megabytes supposedly is optimal. And you aren't paying the cost when you have your data and files that large. You're not paying the cost to read each individual file. On the other hand, more files allow more workers to run in parallel, so that's kind of pushing you to have more files. And it's really a continuum. And I have an example here from a blog post I wrote a few years ago, and some numbers of counting Cloudtrail events. So if you're not familiar with Cloudtrail, it basically tracks most of your activity in your AWS environment, and it stores events as JSON files in S3. So they're readable from Athena. Now, the Chariot environment has a bunch of accounts that get varying levels of activity. We have sandbox accounts for our developers so that they can work out different problems in a constrained space. We have accounts where we develop work for clients that we then potentially turn over to the clients. So we're getting a whole mix of events. You might have at any given event file, it might contain one or two events. The middle of the night, trusted advisor is doing something, or an auto scaling group is doing something, and other files might have thousands of events. That's a wide mix. And when I did this blog post, we had 1.6 million files. So just using Athena to count the number of events, which means it's opening up every single file and parsing the JSON and aggregating the count of events. When I ran it against the 1.6 million files, it took 3 minutes and 15 seconds, which, to be honest with you, is kind of impressive. But then I took all of the files and I ran a process that put events with the same date in the same file. And we had about 2 years of data at that point, so 684 files. With these aggregated files, and again, it's opening up the file, reading all the data, parsing it, and then counting the number of records. It only took 6.3 seconds. So significant speed up by not having that overhead of opening lots of little files. And then on the other extreme, I aggregated all the events into one giant file. And as you can see, the time went up dramatically, again, because it wasn't able to put a lot of chickens on that task. So let me quickly check for questions before going on to partitioning. Nope. So these are two knobs: having the right file type, picking the right file size and the right number of files. And one way that you can really control the number of files is to partition your data, which you incorporate information into the S3 prefix, which will let it only look at certain files when it runs a query. So for example, there's two formats. Typically you have in your S3 URL, you have a bucket, you have a table, and then some number of partitioning values, and then you have files. So for example, my Clickstream data, I have S3, Clickstream data is the bucket, add to cart represents the table name, and then I have it broken up by year and month. There's two formats. This first one is what you get if you use, for example, Kinesis Firehose to write your files. Your second one is what you get if you use Hive or certain other tools to write your files. Athena doesn't really care. It will take both. When you define your table for Athena, you specify the partitions in the table definition. And here's an excerpt of a definition for Cloudtrail events. And up top, you can see it's creating the table and listing the fields. And the fields that it's listing here are all inside the event record. To run against to have a predicate against one of these fields, you have to actually open up the file, parse it. But Cloudtrail events are written with a certain location template, which you can see on the bottom. We have our bucket, we have some literal text, and then it's partitioned by account ID, region, and the ingest date as year, month, day. So I can take those partitioning fields and basically add fields to the table with those names. And the actual table definition is a lot more complex. We're not going to get into that. I'm simply looking at the difference between fields that you have to read the table to get to and fields that are part of the file name. And here's example queries. Simple count, restricted by the account ID, the region, and a range of dates. Here I'm just looking for September 2022. And I run these in two ways. One is I run it where my where clause just looks at partitioning fields. And in the other, I run it where my where clause looks inside the files. So what happens with this is the amount of data scanned, we're now up to, I think, 3-something million files that it has to read. On the left side, it can very easily reduce the number of files that it reads. It still has to open those files and scan them to get the counts of records, but it's far fewer files. It takes 2 seconds to run, 4 megabytes total data read. Whereas on the right side, since it's digging into the files to apply the query predicate, it has to open every single file in our Cloudtrail database, which is currently sitting at almost 14 gigabytes of data, and it takes 6.5 minutes to run. So clearly, for performance, you want the query on the left, but there's one more thing you have to be concerned about. And the query on the left came up with a different count for the query on the right. And I don't know why. I haven't dug into why. My theory is that Cloudtrail wrote a file just after midnight on September 1st that contained an event from before midnight. It makes sense. The file name is what the partitioning used to select the file. So in most cases, this doesn't matter, right? You're off by one out of almost 19,000. For counting queries, on the other hand, it very much does matter if you're off by one, but you can still use partitioning. So if you want the accuracy that you get from the right-hand side, where you're digging into the files for your query predicate, but you want the performance of being able to partition, we can rewrite our query. And I've added in two predicates into my where clause that look at the partitioning information. I've given a much wider band than I need. I want to capture a couple days on either side. But then I dig into those files to retrieve the region and the event time and the actual account ID. Now, I could have added more predicates. I could have, for example, put a predicate on region, the region partition. Account ID is a little bit more tricky because of the way that Cloudtrail deals with account IDs. But just by restricting the files by date, I brought my query time down from 6.5 minutes to 50 seconds, and I cut the amount of data that I read, and I got the accurate count. So you'll find that when you're dealing with Athena, partitioning becomes one of the best ways you have of improving performance. And that might mean that you have glue scripts that take your raw data and split it up into different partitions. That's perfectly reasonable. And this slide I'm going to skip over. I could actually spend 45 minutes talking about these three topics, but there's basically three ways that you can define partitions in Glue and used by Athena. So that takes me to the end of the knobs that you can turn for each. My next page is just to give you a sense of strengths and weaknesses. I've given a performance comparison. A quick check for notes. No, nothing. Okay, so let's roll through performance comparison. Now, I've talked a lot about Clickstream Data, and to do these comparisons, to do the blog posts, I've created basically simulated Clickstream Data for three different tables. The first one is a product page, and as I said earlier, this is when you have someone going to the product page, your e-commerce site generates an event that tracks them going there, has a unique ID, has a timestamp when it happened, and the user that did it. We're not dealing with anonymous users here. Everybody's logged in. And finally, a product ID. Simple data. Real world Clickstream data is a lot more data, but this kind of focuses on the highlights of what you need to deal with. And 60 million rows. And again, this is not necessarily big data. It may seem like a lot of data, but in the real world, I've seen clickstream data of multiple hundreds of millions of rows per month, adding to billions of rows over the course of a year. But this should suffice to give you an idea of the strengths and weaknesses of the systems. So product page, you add your product to cart, very similar event, but now I've added in a field for the number of items you've added to the cart, and 18.5 million rows. So you join these together, they're pretty big joins. And then finally, checkout complete. You've gone through the entire checkout funnel. It's a similar idea. If you have a timestamp when they did it, unique identifier, the user, and then items in the cart and the total value in the cart. And looking at this simulated data is for an e-commerce site that doesn't have big ticket items, but people do like to actually buy them. So here we have 10 million rows. More than half of the people who add something to the cart actually buy it. So for queries, here's a simple query that that basically treats the add to cart as a fact table, and it's aggregating by product ID, the amount of that product added to the cart, and the top 10. Pretty straightforward, single table. For my performance characteristics, I dive into this much more in the blog posts that I've pulled this out of. I have a couple of different platforms that I ran it on. First off, Athena, and I'm using Parquet files for this data. So Athena took under a second to do this, scanning uh, 69 million rows, 60 million rows, sorry, scanning 60 million rows and aggregating. I spun up 2 provisioned Redshift clusters, and one with 4 nodes, one with 8. And the node type that I picked is a DC2 large, which is kind of a good starter node for you if you're getting into Redshift. And it's 160 gigabytes of SSD, 15 gigabytes of RAM, 2 virtual CPUs. Now, the reason I went with a 4 node and an 8 node cluster is the way that Redshift is designed. By doing everything shared nothing, does everything on its compute nodes. Doubling the number of nodes should double your performance, cut your query times in half. As it turned out, it doesn't quite work that way. This particular query isn't perfectly parallelizable because while each individual compute node can do its local aggregation, you still need to pull things back to the leader node to do an overall aggregation. But still, the 8 node cluster, not quite, but almost twice as fast. I also spun up a serverless. Redshift serverless came out reInvent 2021, I think. And the idea is that you're not paying for an always-on Redshift cluster. And the economics are a little bit challenging to work through, but if you have people who are doing things during the day, I think serverless can be a very economical way to go. And it deals in terms of Redshift processing units, which don't map one-to-one to nodes, but I pretended they did. So an 8 RPU serverless cluster, which incidentally is the smallest you can create, was roughly consistent with the provision cluster. And then finally, another blog post, which is why not just use Postgres? This shows you why you don't just use Postgres for decision support. This is not a very powerful RDS server that I'm using for Postgres. I picked it for the blog post to be roughly equivalent to a 2-node Redshift cluster. But still, you have 60 million rows, you have multiple fields in each row. Postgres, because it's row oriented, has to read the entire table to be able to calculate the results. So it's significantly slower. Next up, joining just on the distribution column. The goal of this query is really it's something that Redshift should perform very well because it's not dealing with a lot of columns from the table. So that columnar data store gives you a distinct benefit, and it's a join on a single column that happens to be the distribution column. And the idea here is a user adds something to their cart but never checks out. We want to identify them. So we're looking for cases where either they added to cart after the last time they checked out for people who have bought from us before, or where they've never checked out, people who came to us the first time, added to the cart, never checked out. A pretty reasonable analysis query for your e-commerce site. So in here, the numbers are bigger. We're basically doing a join between a 19 million row table and a 10 million row table. So again, I was a little bit disappointed with the 8 node provision cluster. I expected it to take half the time as the 4 node cluster. It didn't. On the other hand, the serverless cluster was about half the time. And I should note here that I tried my very best. All database systems have caches built in. I tried my very best to prevent those caches from skewing the results, including doing such things as rebooting the Redshift clusters between running the queries. And then Athena comes out quite respectable here, 4.5 seconds, equivalent to the 8-node Redshift cluster. And this, I think, is because this is a larger job. It's simply giving you more chickens to do the work. Now my final comparison is a multi-column join. This you've seen already. It's looking for the difference between the number of events where people looked at a product and they added it to cart. And this is starting to make Redshift play against Redshift strengths because we're dealing with multiple columns from the table. So the columnar data store doesn't really help you so much with Redshift. And the join, again, we're joining on user ID, not which is a distribution column, so no problems there. And we're including product ID in the join, so a little bit more data that has to be retrieved, hashed, and then compared. And coming out of this Redshift, I'll be honest, disappointed. It took, as you can see, 30 seconds for the 4-node, 24 seconds for the 8-node. Serverless, quite respectable. But again, I don't know how much of that might be due to caching effects. And then Athena was the big surprise here. Athena just, as far as I can tell, you're joining 60 million rows to 20 million rows. It gave more chickens to do the work. So that should give you some ideas about what you pick. I have become much more of a fan of Athena over time. But let's talk, just to wrap up, about the summary. So architecture, just the points. Redshift's a traditional database. It's based on Postgres 8. People make the mistake of saying it's a Postgres 8 database, but really, as far as I can tell, the only thing that it has with Postgres 8 is its query parser. Everything else is unique to Redshift. That means that certain features that you have with newer databases aren't supported. Fixed nodes, you're basically, whatever you pay for is the compute you get. And then the key thing is you have to distribute your data properly to do joins. Versus Athena, structured text, you can get to that data any way that you want. You could do glue jobs, you could download it and use JQ to parse JSON data. And the key thing here is variable number of workers. We don't know how many workers it might pick for any given, we don't know the rules, but we know that it's going to add workers as it sees fit. And then the knobs, Redshift, distribution key, sort key, compression. And you get a surprising amount of capability out of that. Athena, file type, file size, and the big one is partitioning. And that wraps me up. For more information, I believe that we'll be sending a copy of this talk to people who have signed up. So hopefully you might find these links interesting. Some of the posts that I've written for Chariot, especially the right sizing data for Athena, which is looking at Cloudtrail events, and then some AWS documentation links and blog posts that I've found useful. And then finally, to repeat what Becca had said earlier, we are doing an office hours program. So you can scan this QR code or click the link that she put in chat. And it's just basically a one-on-one to discuss big data. Hopefully something, bounce ideas, talk about what problems you're running into, hopefully get some value out of it.